Okay, let's turn now to the second half of the problem. The first half of the problem is energy transfer from the lattice to things within the lattice. And I guess I think on a theoretical basis now, I think we've got a rather good understanding as to how it could work, how it would work, how it ought to work theoretically. In the case of heat production or tritium production, you need another bit of physics. Namely, if you have a claim of heat production, you might say that maybe it's experimental error, maybe it's chemical reactions, or at least that was what was said early on. The chemical reaction explanation is a little bit tough because the amount of energy that are involved in these claims corresponds to more than 50 times the amount of energy you'd get if you turned your cathode into TNT and detonated it. You can't stow that much energy chemically. The amount of energy production corresponds to several hundred electron volts per atom, up to a kilovolt per atom. And this is from quite a few laboratories, including SRI. You could say it's experimental error. That's still said today. And when all said and done, I actually don't believe it. However, it behooves the folks in the community to continue doing careful work and sending papers and getting them published and so forth. So we can do stuff with them and get it so we can replicate the experiments easily. The situation is very much improved now relative to 1989. Could be better. Consequently, if you think it's real and it's not chemical, then it's got to be nuclear. In the case of nuclear reactions, there's fusion, fission, and weak interaction reactions that are known. I've talked about something called lattice-induced reactions, and that's where the lattice transfers the energy and makes some of these things happen. I've been thinking of a new kind of reaction, which I'll call a neutron transfer reaction. The basic issue is that if you're going to have heat production, you need heat production as first suggested by Pons and Fleischmann. It was proposed that it be DD fusion. And it was posed the question, can this be feasible? This was looked into by the nuclear physicists. The view graph's not here. Anyway, the answer is that in 1989, given what was understood about screening theory, the answer was no. You can't have DD fusion happen at rates that would be commensurate with what Pons and Fleischmann were claiming. Since that time, there have been quite a few papers where the screening between deuterons and the lattice has been studied at great length. Perhaps the most extensive has been a paper by Ichimaru, published a year and a half ago or so. And he calculated screening rates that impressed quite a few folks. Nevertheless, at the end of the day, the screening wasn't enough to allow you to have fusion reactions at the rates that we required to explain heat production and tritium production. Now, the basic problem with that is that the Coulomb barrier keeps the nuclei away from one another. So it's hard to have nuclear reactions when you can't get the nuclei to hit one another, touch one another. I proceeded along the lines of a different point of view. And the different point of view involves neutron hopping, and it involves neutron hopping coupling through virtual states. The basic idea in laser physics, there's something called real transitions, where you start from one state, you tune your laser, you drive your population to another state, and then it decays down to yet a lower state, or maybe a higher state, one way or another. So this is a standard experiment folks might do in laser physics. If I were to think of neutrons being bound and being free, and take that picture and redraw it in the case of neutron physics, assuming for the discussion here that maybe I had a gamma ray laser. If I tuned a gamma ray laser up above the ionization energy, I could make free neutrons. And those free neutrons would decay and give me a gamma. So this and this would be analogous processes. In laser physics, I know that if I drive a transition off resonance, I could still see population. I can still see emission, and the emission will correspond to a frequency that's not the difference in energy, but corresponds to the difference between the virtual state here. To some degree, laser physicists know that you can establish virtual populations of virtual states. If you made the same argument here, then you might say you start from the first state you go to continuum states, but you pump them with not enough energy to make them free. And if they manage to get over here, then they'll go down and decay and give you a gamma. Of course, you could never do that because you don't have a gamma ray laser. On the other hand, if you have a DC field, you could imagine coupling the neutron from here to a state far below the continuum. Be continuum orbital, but it'll have much less energy than the continuum. And then you can imagine getting out gamma emission at this frequency. Now, in principle, this could be done because you have DC fields. A magnetic field in principle might be able to do something like this. The basic idea for heat production would be to take this basic type of mechanism and have the lattice take up the energy when the nucleus first leaves through the kinds of mechanisms which I was described earlier. In this case, then, this is a resonant transition, and this can happen with a very high reaction rate. Now, I constructed a theory for this, and Jean's going to come down and strangle me if I show very many more of these few graphs. But the basic issue is when nuclear physicists calculate their nuclear wave functions, there's something called an independent particle model, and then there's things that are better than independent particle models. And the basic idea is that when the nuclei move, they move in such a way that their relative motions are correlated with one another. In the grand scheme of things, the only way the nuclei are able to do that is if some of the nuclei end up spending some of their time in free orbitals. Now, if you only have one nucleus, that doesn't lead to anything because all of the contributions in the free orbitals, they destructively interfere. So you get the same answer you would have gotten if you didn't even know about it. But in the case of a lattice, you've got many nuclei at the different lattice sites all talking to one set of continuum orbitals. And it turns out the physics of that gives rise to equations that are the kid sister to what's known as the Anderson model or one of the Anderson models in condensed matter physics that describes heavy fermion systems. Basically, electrons hop from site to site in semiconductors and metals. And the essential proposal here is that the interaction of the nuclei with each other leads to the possibility of a very tiny second-order effect that is the kid sister of the electron hopping. It would be neutron hopping from site to site within the orbitals.